All right, fantastic. Well, thank you for the introduction. We've been happy to work with Buckley and all of your customers, engineers, contractors in the Boston and New England area for years. Buckley does a great job, and we're very proud to be part of this presentation with the Buckley team. We're going to tag team today, and as Matthew said, this Matt has been here a long time. I'm right pushing about 30 years with Greenheck Fan Corporation, mechanical engineer from University of Wisconsin. And most of my time has been related to product marketing and product development and training on applications like laboratory exhaust, smoke systems, all different types of HVAC applications. My partner in crime today is Mr. Justin Zahn, and I'll let Justin introduce himself and kick us off as we go through our agenda this morning.
All right, thanks a lot, Matt. Well, I have not been at Greenheck for 30 years, I can tell you that. I have been at Greenheck for right around 3 years. My main job is to work in our laboratory and fume exhaust line. I actually come from the generator world. So before this, I was an account manager with a generator company. So, you know, kind of flip-flopping in between industries for sure. But we'll kick it off here. There we go. Today, we're going to talk just a little bit about basic lab exhaust system guidelines. We're going to go over the basics of operation. We're going to actually switch to our virtual lab here shortly, which is a nice break, I guess you could say, from the PowerPoint, and then we're going to go over best practices. So what is the point of a laboratory exhaust system? We want to remove any effluent or contaminant coming from a space below, whether that's a lab, an isolation room, an OR suite, whatever it may be, and we want to expel those fumes up into the atmosphere as far and away as possible. The biggest thing is going to be we want to prevent any re-entrainment into building makeup air systems. So we want to make sure that our plume height is high enough where we don't have any issues with that plume coming down too soon and running into a building makeup air system or the general public below. These are life safety applications, so most of the time whatever these fans are exhausting is extremely hazardous to the general public and sometimes even deadly depending on what's coming out of that space below. So our whole point, again, get those hazardous fumes out of the space below and expel them into the atmosphere and expel them at a rate high enough where there's not going to be any issues with that coming down too soon and running into any building makeup air systems. We design our fans around two key standards in the industry. The first standard is going to be ANSI Z9.5, which states that these fans needs to have a discharge velocity of 3,000 feet per minute or more. Okay, most of the time, depending on what plume height you're going for, it could be a little bit more than 3,000 feet per minute, or it could be a little bit less. That standard is actually now changed in the industry. That standard is now up to you, the designers of that lab space, to determine what kind of velocity you need coming out of these fans. Most manufacturers are still going to recommend at 3,000 feet per minute or more, just because we know it's safe, we know it works. I mean, it's been used for quite a while. One reason behind that change, though, on why it's no longer 3,000 feet per minute is, I think it kind of goes without saying, but these fans are energy hogs, right? They take a lot of energy to run. So if you don't have to have your fan running at 3,000 feet per minute, why would you, right? If you can save a little bit of energy, whether that's at 2,000 feet per minute, 2,500 feet per minute, or whatever works for that particular application, that's what you should do nowadays. You don't have to follow that 3,000 feet per minute anymore. Again, most manufacturers are still going to recommend that 3,000 feet per minute just because we've been using it for so long and we know it's safe, we know it works, and these are life safety applications. So we want to make sure that we are being as accurate as humanly possible when it comes to the plume height and the discharge velocity. So that's ANSI Z9.5, standard number 1. Standard number 2 is going to be NFPA 45. So that states that these fans need to be 10 feet tall from the roof deck up. Okay, you really won't see a laboratory fan under 10 feet tall. And reason behind that is because for the people working up on the roof, we want to make sure that they are 100% safe. Okay, we want to make sure that they are not having to worry about coming in contact with whatever is being exhausted out of that space. And we also, want to make sure that when people go up on the roof that maybe aren't too familiar with these laboratory exhaust systems, we want to make sure that they don't have a chance, to stick their hand or their face or, whatever else over these fans. Because as we said before, most of the time, whatever these fans are exhausting is extremely hazardous. And if they come in contact with whatever's being exhausted, could potentially, be deadly. So we want to make sure that, 10 feet tall minimum, that's what we're sticking with. Obviously, as I'm sure a lot of people know, when it comes to the 10-foot tall rule, we sometimes run into issues, mainly with architects. We think these fans are beautiful. They do not so much, just because they are 10 feet tall. Most of the time, they are much, much taller than that. So it is a constant battle. But again, the 10 feet tall rule is something that we won't budge on. We want to make sure that we are following that standard to a T. It's a common question we get a lot. Can you make your fans 9.5 feet tall, 9 feet tall, whatever it may be? The answer is always going to be no. So those are the two standards: ANSI Z9.5, 3,000 feet per minute, and then NFPA 45 at 10 feet tall systems. So moving on here now, we assume that everyone knows what AMCA is. For those of you who maybe don't know what it is, AMCA is a third-party testing service that basically all the information that we give to Buckley, who then passes out to their customers, the AMCA certifies that data that we pass out to to our reps. So it's a good way to determine how a fan's going to perform once it actually gets out into the field. It's kind of a peace of mind type of deal. There's not going to be any surprises just because it was third-party certified. Why I'm showing you this slide right now is because there are two different ways to say you're AMCA certified. One is incorrect and one is correct. A lot of people, when they hear that we're tested, there's still some manufacturers out there that say, we're tested in accordance with AMCA. That does not mean they're licensed to bear the AMCA seal. So that AMCA seal here is going to be the sticker on the left side here. You want to make sure that they are licensed to bear that AMCA certified rating seal. When people hear tested in accordance with AMCA, they sometimes go blind. They hear AMCA and they think, oh, we're good to go, but that is not the case. There are still some laboratory exhaust products out there on the market that are not AMCA certified. And because of that, that is slightly concerning, and we want to make sure that people are aware of that. Again, we want to be as accurate as humanly possible with these systems and our data, just because these are life safety applications. As I said before, being AMCA certified is a way to certify that data. And not being AMCA certified, if someone's just tested in accordance with AMCA, that does not mean they're AMCA certified. That does not mean that data that's been put out to you is 100% accurate. I'm not saying it's not saying that people are going to skew their data by any means, but it just means that data is not certified. Okay, so we just want to make sure that people are aware. There are still products out there that are not AMCA certified, that don't have that AMCA certified rating seal. And it's important that you as customers ask questions. If you hear someone say we're tested in accordance with AMCA, pick at that a little bit. Ask, are you AMCA certified? And if not, why not? It's always important to ask that question, and you want to hear them say, they're licensed to bear that AMCA certified rating seal. So moving on here now, we're just going to talk about some, I should say, the best practices when it comes to the overall design of these laboratory exhaust stacks. We always want to stick with straight stacks with conical nozzles. Okay, so at the end of the day, this is not rocket science. The whole point of these fans is to achieve a higher plume height. Whether the plume height's going up 30 feet, 40 feet, whatever it may be. We want to make sure that we are not designing anything on this system that can negatively impact our plume height. And sticking with straight stacks, nothing on top of these stacks, so no caps or anything like that is the best practice. We're going to move down here to the bottom, and sometimes people will laugh when they see this gooseneck gooseneck stack on this screen, but you'd be surprised. We see some pretty wild wild designs out there in the industry right now. We just simply ask everybody, plain and simple, please don't do this. We ask you, please don't put that gooseneck on your laboratory exhaust system. It completely defeats the purpose of what we are trying to achieve with these systems. Again, we want to achieve that high plume height. We don't want to dump whatever we are exhausting straight back onto, you know, the roof or the ceiling or the rooftop or whatever it may be, or over the side of a building where it could come, you know, in contact with the general public. We also want to avoid putting caps on these stacks, just because, again, that would negatively affect your plume height. Straight stacks, again, conical nozzles, we don't, you know, it's not complicated. We don't want to make these systems any more complicated than they need to be. Again, straight stacks is what we recommend, and please avoid the gooseneck at all costs. Moving on here now, we're going to talk about two different ways to calculate plume height. There are two different calculations currently in the industry right now. The first one you're going to see on the screen here is going to be the modified Briggs equation. Fairly simple equation. That equation is now more or less, you could say, being pushed out of the industry just because it's not nearly as accurate as the momentum flux equation. Okay, so the momentum flux equation, the main difference between these two equations is going to be your terrain categories. Okay, so where these fans are going, that has a direct effect on your plume height. Whether, you know, if it's going downtown Boston or if it's going to be going in the middle of nowhere, that's all going to have an extreme effect on your plume height. For downtown Boston, for example, as I'm sure everybody knows, you know, the taller buildings, that wind bouncing off those buildings, the taller buildings, will cause some type of turbulence, which in return, if there's some tall buildings around one of our laboratory exhaust units, that's going to have a direct effect on that plume height. Okay, whereas if it'd be in the middle of nowhere, you know, plume height wouldn't be so much of a concern. And, you know, the terrain categories really wouldn't, you know, it wouldn't really come into play as much, just because, again, there's not going to be anything that's going to affect that plume height. Why I'm showing you this slide is we want to stress the importance of sticking with momentum flux. Okay, we want to stick with momentum flux just because it is far more accurate compared to the modified Briggs. And with modified Briggs, we still see it used a little bit in the industry. And why we see it used in the industry is because using modified Briggs typically gets you a higher plume height. Okay, but it's important to remember that that plume height is not nearly as accurate as it would be using the momentum flux equation. And we want to stress the importance, again, using that momentum flux equation. And if you see something, if you're trying to decide between two manufacturers in the laboratory exhaust market, and you see one, you know, manufacturer that has a plume height that's, you know, 10 feet higher than competitor X or competitor Y or whatever it may be, it's important that you question that. You know, ask what kind of equation they are using. In our experience, we keep both momentum flux and modified Briggs in our selection programs. We default to momentum flux, but we keep modified Briggs in there for one reason, and that is, you know, when we see someone, you know, that portrays a 10-foot higher or has a higher plume height than us, you know, we simply switch it to modified Briggs in our selection program, and we're usually dead on the money every single time. So at the end of the day, this is not rocket science. Okay, if you have, you know, same fan, same wheel, it doesn't really matter who you're going against. The plume height should be relatively close to the same.
All right, Kate, thanks, Justin. The other little item that you see with momentum flux that is a little unique is that the Briggs equation gives you a point of height above the nozzle. So as Justin said, you're going to get the stack height's going to be like 20 feet tall or 30 feet tall of plume. What momentum flux adds now is what happens if there's a wind blowing, and what does that plume rise do over a distance? So if you play with, you know, our selection program that has momentum flux, you're going to find that we'll print out a chart that shows how high does that plume get, in this case 120 feet away from the stack. So as you're closer to the stack, that's what this blue line represents. You know, so at 60 or 70 feet, I have 14 or 15 feet of plume rise. But what they end up doing is, it's a pretty conservative equation set, they're going to have a stacked cap factor. So in this case, as you get 70 feet or further downstream, it's going to say your max plume is going to be, in this case, just a little over 14 feet tall. So when you look at your effective plume height, you take the NFPA 45 number that Justin gave you, which was at least 10 feet. You'd add the 14 feet, and what our selection program would say is you have a 24-foot, plume rise. Plus, then we would introduce how that changes over time, at a distance. The other thing now that's available to you through ASHRAE is a plume concentration modeling tool. So while the momentum flux is much, much more complicated, than a simple momentum equation from Briggs, it gives you a lot of cool little things you can play around with. And you could go into the ASHRAE catalog and do all of these formulas, but we've embedded that as part of our program now, so you could take an introductory shot at making a fan selection and checking out what that plume concentration would look like. So we have the stack here on the left, and you can see the effective plume rise, that black curve coming out with different color bands telling you the amount of concentration of effluent, as you separate from the main stream of air coming out of the fan. So if you're 60, 90, 120 feet downstream, upwards of 40 feet above the roof, maybe there's an air intake somewhere 20 feet above the roof deck. What this model would show you is that you're in pretty good shape. You don't have to worry. If you're 120 feet down and your air intake is 80 feet, you might want to go to plan B and figure out how do you either get that plume rise higher or deal with the location of that air intake. This doesn't replace talking to a wind wake consultant, but it is, an ASHRAE set of calculations that you can use, and like I said, gets you your preliminary design rolling before you would start talking to a wind wake expert. A little about the labs. There's two different big changes that Justin and I are seeing and what we're dealing with more and more. If you go back 20, 30, 40 years, you would see that a lab looks like what we're showing here, where you have multiple chemical fume hoods with their own individual riser, and they would have generally like a little power roof ventilator, a little utility set up on top of the building. In many cases, those utility sets they weren't 10 foot tall. You could just walk up and feel the air on you, and they could have been contaminated. So the pros and cons of that system is that if one of these hoods isn't pulling the appropriate amount of air, you could track up to the fan and maybe find the fan isn't turned on, or the belts are off, or it needed some type of maintenance. On the other hand, now when you have 50 hoods and 50 fans, there's a lot of maintenance. There's a lot of roof penetrations that you have to deal with water and such. And the other thing that happens is that when you're looking at a small flow of air and you think of this as a momentum problem, you have a hard time getting these small little fans to give you a high plume rise. So the roof decks can be unsafe, and contaminated air can get back into your building. So a major change that we're seeing, and most of the jobs we're working at now are going from those individual fan and stack systems to manifolded systems. So you as engineers, as you're designing, you're probably doing more and more of these, where you take fume hoods that are doing, like type reaction, they're doing the same type of research. So it's, it's all basically the same stuff. We're pouring it into one common duct now. And instead of 50 little fans, we're using 2 or 3 bigger fans that can take all of this air from these hoods and combine it and give you a much, much higher plume rise. But you have less fans to maintain, less roof penetrations, all good stuff, which can be an advantage to your operation of your system. And we're going to talk about how this saves energy here in a few minutes as well. Now, you got to be careful because some chemicals don't play nice with each other. So while we're combining a lot of the hoods that are doing common research, we still have hoods off to the left that might be doing perchloric acid or radioisotopes, things that you don't want to intermix with the rest of the general labs because it'll contaminate the system and cause problems. So in many cases, we'll see a lot of hoods tied to our fans, and then you have a couple individual fans off on the side doing their own thing. So we don't have problems with reactions inside of the ductwork. So what we're going to do quick on that note and on these manifolded systems is talk about our virtual lab. And before I proceed, Matthew, I just want to validate you're seeing the same screen we are with our virtual lab and airflow and anything's moving?
Yep, we can see it.
All right, Justin, take it away.
Okay, sounds good. So on the screen here, you're going to see your typical lab setup, right? You have, a couple of fume hoods, snorkel, storage cabinet, all going up into some kind of common ductwork and then up into the fan.
Hey, Justin, one sec. It's not moving anymore. It was moving, but now it's
Oh,
not.
it's frozen.
Yeah.
So make sure you move that thing back. Just
yeah. Okay.
Oh, there. Oh,
It's
you know what?
moving now.
It's moving now.
I just have to
Yep.
move it up so you can see. Oh, when we okay, we're good, I think.
Okay. All right. Sorry about that.
No problem.
So talking about, the lab and the overall space below, before we actually, start getting into the fans, there are 3 control loops that stay the same throughout every lab, that you'll encounter. First control loop is going to be the face velocity. So the hood velocity, the air moving across these hoods. Typically that's going to be around 80 to 100 feet per minute. You usually won't see anything too much faster than that. If you do, you run the risk of ruining whatever you are working on in that space. So typically 80 to 100 feet per minute is what we see. So that's control loop number 1. Control loop number 2 is going to be how you pressurize your space. So that air coming back down into the space, typically that's going to be a negatively pressurized space. You will run into different situations where it may be positively pressurized. Mainly OR suites, from what we see, would be positively pressurized, but usually that's going to be a negatively pressurized space. So that's control loop number 2. Control loop number 3 is going to be your duct static. And how we control that is through our bypass damper. So as people go home for the night, hood shut down, you're going to notice that this light here turns to red. As that turns to red, we need to relieve some of that duct static by modulating open our bypass air damper, okay? So that's how we control that. Along with that, when that demand from that lab space decreases, we usually, these fans are going to be a constantly running system, okay? So they're not, and the space below is going to be a variable system. So when the demand from that lab space changes a little bit, we need to make sure that we are, in order to maintain our set, plume height or velocity or whatever it may be on these fans, we need to make sure that we are able to pull in some extra air. And by doing that, we utilize our bypass damper. A lot of people have questions on when it comes to the bypass dampers of these systems. For those of you who are not too familiar with the laboratory exhaust system, or for those that we have worked with that are not too familiar with the laboratory exhaust system, these bypass dampers are sized a bit smaller compared to maybe what you have seen on other systems. And the reason for that is because we want to create velocity going through these systems. Okay, so to do that, we size our bypass dampers just a little bit smaller and creating that velocity. So when we modulate that open, we know that we're still going to be able to maintain our targeted plume height or targeted outlet velocity. So again, the 3 control loops, just to reiterate, it kind of went off course there a little bit, is going to be your hood velocity, so 80 to 100 feet per minute, how you pressurize your space, and then your duct static here.
One thing I'll add too, because I know Antec is going to be talking to you this afternoon. One of the things that Antec will talk about, and from our perspective, from the fan side, our portion of what Justin was talking about is making sure that duct static pressure stays at a negative level. And we'll talk more about this when we get into the controls. But where an Antec will fit in now, they're the valves on top of the hoods, as well as the supply side. So, they're controlling that room static pressurization, and they're helping maintain that velocity. So our little valve opens and closes here based on the sash position. And you're going to get a lot more of that detail this afternoon. What we're just trying to make sure is that there's not too much negative when these sashes close, that there's not too much negative pressure that would cause the valves to break or the duct to implode, all things that would make us have a bad day. So that bypass damper is really, really critical in the operation of these entire systems. So Justin, I'll let you go back through the fans.
Okay, awesome. Thanks, Matt. So talking now about the fans themselves, on the screen here, you're going to see your typical laboratory exhaust fan, probably the one that people associate lab fans with the most. It's going to be some type of mixed flow fan. All right. So the advantages to these types of laboratory exhaust fans is you're going to notice the footprint of these fans is fairly small. Okay, so you can have a smaller footprint while being able to handle, you know, large amounts of CFM. These fans are typically capable of anywhere from 80 to 85,000 CFM up to about 8 inches of pressure. Okay, so they are built for larger jobs. You will see them on, you know, hospitals, biomedical facilities, any job that requires, you know, higher CFM capabilities, higher pressure capabilities is where you're going to see this type of fan. A couple of key design points when it comes to the mixed flow fan. On the screen here, you're going to see our direct drive option. A lot of people who are not all that familiar with laboratory exhaust systems think that this motor actually sits within the airstream. It does not. That motor actually sits within a bifurcated housing, so you can kind of see it's a double wall housing essentially, where that air actually moves up and around that motor and then into the nozzle, into the atmosphere. So that motor is completely isolated from the airstream, which is a good, good design point to these fans, just because one, it prolongs the life of these motors. And on top of that, maybe the more important part of it, it keeps people safe. If they need to work on these motors for whatever reason, replace it or whatever it may be, they don't have to worry about coming in contact with whatever's being exhausted out of these systems. One slight drawback to these types of direct drive fans is where that motor does sit. Obviously, it's a little bit harder to get at, okay? But because it is a direct drive option or a direct drive unit, there's going to be less maintenance to begin with. Most of these fans come with 12-month lube intervals, so very little maintenance. Obviously, these are mechanical systems, so anything could happen, but if there's not any problems or any issues going on with the system, it's very little maintenance on these types of systems or direct drive units. Whereas your belt drive fans, and I don't believe we have an image of a belt drive Vector M on this or a mixed flow fan on this until we get to our redundancy talks, but the belt drive option, it'll sit in a conduit box or a box on the outside of this fan here. And it'll be a little bit easier to get at, but because it is belt drive, it's kind of a trade-off. Easier to maintain, but more maintenance is required on that. So, we have reps that have customers that, only want belt drive for the ease of maintenance aspect. And then we have reps that have customers, that only want direct drive because there's less maintenance. There's less maintenance that's required. Obviously, there's jobs that require, direct drive, or there's jobs that require belt drive. But the jobs that go one way or the other, sometimes it does come down to preference on there. Moving on here now, we're going to talk just a little bit about the isolation damper. So the isolation damper, where that's located, is actually above the plenum, which may be a little bit different compared to some of the other fans that are out there in the industry. The isolation damper is definitely one of the more important pieces of these systems. And why I say that is because if you're running some type of redundant system, so N+1, N-1, which we'll talk about in a little bit. If you're running N+1, so let's say you have two fans, on one system on a common plenum, you have one fan that's off. You want to make sure that that isolation damper is 100% perfectly sized, for that system. So the fan that's off, you want to make sure that that isolation damper is 100% sealed up tight, so there's no risk of having air being pulled back down through that system and then spinning that fan backwards. Another, key point to make on this is we get a lot of questions about using, specialty dampers in our fans. The isolation damper is usually one that, we really try to push back on, that we don't want to, include a third-party isolation damper in these types of fans, just because, again, these isolation dampers are 100% perfectly sized based off, the information you give your reps. Okay, so there's no guessing involved. I guess that's kind of the main point we want to make on this. And having these perfectly sized is critical to having a successful application. So that's a little bit about the mixed flow fan. We are now going to switch to the Vector CH. And Matt, I just want to confirm that it's still moving on your screen, correct? I'll take that as a yes. Okay. So this is going to be the centrifugal style type laboratory exhaust unit that we really like to push in the industry, especially on larger jobs. These fans are capable of 140,000 CFM up to about 13.5, 14 inches of pressure. So they are built, again, for larger jobs. A couple of key selling points to these fans is they're going to be slightly more efficient than your typical mixed flow laboratory exhaust fan. And the biggest thing that a lot of customers like is going to be where that motor is located. So hopefully everyone can see my mouse here, but that motor is located right at roof deck level. Really easy to get at, really easy to maintain. And obviously, I'm sure everyone knows that it's getting harder and harder to find people that actually want to maintain these fans. So if you can sell an ease of maintenance point, that's always a good selling point, I should say. Whereas if you look at your typical mixed flow fan, it doesn't really matter what manufacturer you're going to, maintenance is going to be a little bit more difficult on those types of fans. So when we can, we definitely want to push the centrifugal style type laboratory fans. But as you'll notice, one slight drawback to these types of fans is going to be your footprint. Okay, so these systems can get extremely large, and with all the other systems up on the roof, sometimes it's just simply not in the cards. You're not able to have this type of system on the roof, and that's where you would need to go to a mixed flow style fan or that inline fan with that smaller footprint. But again, for larger jobs, when we can push this and there is room up on the roof deck, this is usually where we like to start. So next, what I'm going to talk about, and I can leave this fan up on the screen. We're going to talk about just the different types of nozzles that you will typically see in the laboratory exhaust world. The first type of nozzle you're going to see is your high plume nozzle. Okay, nothing too crazy about it. You're taking a large space, condensing it down into a smaller space, creating that velocity. Definitely one of the more efficient options when it comes to the laboratory world. But most people, when it comes to laboratory exhaust fans, they think dilution, okay? And there's nothing wrong with that. Definitely the dilution nozzle is one of the more popular options out there in the industry. This can be utilized, or this type of nozzle can be utilized if you have an exhaust with a really, really bad odor, a really, really hazardous exhaust. And if you're in a highly populated area, this is a great way to knock that exhaust down a little bit so it's not as hazardous, or it doesn't have that bad of smell by the time it actually hits that atmosphere. You're going to notice on the screen here, we can get up to 218% more dilution by just using the nozzle. That is a calculated value by AMCA. That's not an estimate. So just by using this nozzle, you can get up to 218% more dilution. Obviously, when you start training some extra bypass air, then you're looking at close to 300% more dilution, depending on how much bypass air you are actually pulling in. So again, it's a great tool to use, but because we are in training more outside air, so we're moving more air, what do you think happens to your brake horsepower? It goes up, right? Because you are using more, a little bit more energy. On top of that as well, the system with this type of nozzle is going to be a little bit louder or noisier, I guess you could say. We do have ways to combat that noise, but as cities grow, populations grow, no one wants to listen to these fans, so noise is becoming more and more of an issue. Whereas if you look at the high plume nozzle that I talked about before, it's not going to be as noisy, and it's going to be a little bit more energy efficient, okay? We like to tell people we're trying to change the narrative in the industry. A lot of people look at laboratory exhaust fans, they think you have to have a dilution style type nozzle. That is simply not the case. We want people to do your homework in kind of, look at all different types of options where if there may be jobs where you can go to a more efficient option and look at that high plume nozzle and not have to go to that dilution style type nozzle. Again, we're not discrediting the dilution nozzle whatsoever. We're going to talk about it a little bit more in the next session. But the whole point behind this is do your homework. Can you get away with the more efficient option with the high plume, or do you need to go to that dilution style type type nozzle. All great options. Obviously, the dilution style nozzle is extremely popular in the industry still, but what we're trying to change is, you don't have to have dilution. There's no code in this industry that says you have to have dilution. So moving on here, we're going to talk really quick about the two types of redundancy that you will see out in the industry. We'll discuss this more in depth in the next session, but real quick. So the first type of redundancy, the more popular type, I think you'll see in the industry is N+1. You have one fan on, one fan off. So one fan fails, this other fan will automatically ramp up and take over this fan's load. One thing with N+1 redundancy, you'll notice that the fan that's off is 100% shut off. Okay, so there's a little bit of a lag time, especially on larger systems, for this fan to ramp up and to fully take over this fan's load. Why that can be a concern to some people is because, especially with larger systems, when it takes a little bit to ramp all the way up, there could be some system, or I should say minimal system effect down in the space below. Okay, so it's something to think about. Whereas if you look at the other type of redundancy, mainly on critical applications, you'll see this, N-1, you'll have both fans running, both fans taking around 50% of the CFM coming from the space below. One fan fails, and then this fan will automatically ramp up the rest of the way, all the way up to 100%. One thing to keep in mind with this is with N-1 redundancy, this fan that just ramped up the rest of the way to 100%, let's say it was running at 50%, that fan, we call this a hot standby. Okay, so the ramp up time is much quicker, just because this fans are ready at 50%. But one slight drawback to N-1 is we talked about earlier, we want to create velocity going through these systems, right? Because each fan is only running at 50%, we need to now create a little bit more velocity going through that system in order to maintain our targeted plume height. One way we do that is by narrowing the nozzle diameter a little bit. So narrowing the nozzle diameter would mean if one fan fails and the other one ramps all the way up, that now we have to push all of 100% of the CFM up through a much smaller diameter nozzle, which in return N-1 would require a bigger motor. So the upfront costs are a little bit more compared to N+1, but N-1 does tend to be the more efficient option out there in the market. And again, you'll see this on mainly critical applications where we can't afford to have any type of system effect going on down in the space below. So one other thing I'm going to talk about here really quick is going to be attenuation. So as we talked about earlier, these fans are on the louder side, okay? But there are ways to combat that sound through the attenuated wind bands, the inline attenuation, and then the bypass attenuation. You're going to notice there are, different types of attenuation that people may prefer. One, we'll start with the attenuated wind bands, okay? Adding that attenuated wind band will sometimes avoid adding guy wires because your system's not necessarily getting all that much taller. Whereas if you look at the inline attenuation, we added a decent amount of height to the system now, which then in return could require guy wires. No one wants to deal with guide wires nowadays. Usually where I like to start, earlier we talked about the bypass damper and how small that is, and it's because we want to create velocity. Where I like to start, depending on how much bypass air we're planning on pulling into this system, I like to start with the bypass attenuation, okay? Because our bypass dampers are, sized a little bit smaller, when you modulate those open, it really hums, okay? It's not a quiet part of the fan whatsoever. So, combating some of that sound with the bypass attenuation is we're combating one of the louder parts of the fan for sure. And on top of that, your system's not getting taller, so you won't have to worry about guy wires. But again, it kind of comes down to, how much are you planning on modulating that bypass damper open? Are you going to be pulling in a significant amount of bypass air? If not, then it may make more sense, to go to an attenuated wind band or the inline attenuation. But nonetheless, we want to let people know that there is options out there. And again, avoiding guy wires is usually a good idea. I haven't really worked with anyone yet in the industry that likes dealing with guy wires. So if we can avoid them, we definitely want to do that.
If you want to go back to the redundancy, I want to,
Sure.
so we have 1 minute here. One of the things that Justin talked about as well, and when we talk about N+1, N-1, I'll just go to the N+1. And I'm just going to reiterate the comment he had on these isolation dampers. So, he'd mentioned below, between the bypass plenum and each fan, you have an isolation damper, one on the left and one on the right. And when fan number 2 is not running, it's absolutely critical that that damper is sealed shut. And when Greenheck got into the lab business 25 years ago, complaints that we heard in the market were that other manufacturers had dampers that just weren't robust enough. And if you have a system that's pulling 4 or 5 or 6 inches of pressure, any leakage backwards would deflect those blades and they would just lose containment in the lab. So, when we're talking about specifying and having products that are going to work, you definitely want to specify a heavy duty control damper as part of your isolation damper package. So you're going to see high velocities, high pressure, and any time we can keep flow from going backwards through your down fan is extremely important to the overall performance of the system. So Justin, anything else we need to cover on this? I think that's the big stuff.
Yep.
Maybe one little thing I can key up here, which is a little lead on to the second part of this is, along with the controls operation, we're going to talk a little about decarbonization and knocking down the energy. And Justin mentioned a couple different control loops. And why do we have a bypass? Why are we shutting the airflow down? So the highest way, one of the primary reasons that we see these variable volume lab systems becoming more in vogue is that it's an energy savings tool as well. So when you're in this situation and it's 100% exhaust, so that all your sashes are open, and Justin mentioned the pressurization in the room. We generally want to maintain negative static pressure. So in the simplest terms, we have more red arrows leaving this space than blue arrows coming into that space. My bypass damper is closed, the fan is getting the appropriate flow. But one of the items that you get with a variable volume system is that when you start closing your sashes, now I go from 3 arrows to 1 arrow because this little valve is working. Now I have less red arrows, and now watch the blue arrows. The idea here now is when you close that fan and all of these sashes down, less air out of the space means I have less air that comes into the space. So even in Wisconsin this week, we're going to hit close to 90 degrees. It costs a lot of money to take all that 90-degree humid air and dehumidify it and get it the temperature to what you need in that lab space. So safety is obviously extremely critical. The idea, though, of being safe plus reducing the cost of energy is extremely important as well. So that'll cue us off to what we're going to talk about in the next hour. What we're showing here is the most fundamental version of that, but there are other techniques as well that we can utilize to make sure that we're reducing the cost of operation. So I'm going to go back to our presentation here, which we should be at. Slow a little bit. So Matthew, if you're not seeing the presentation, let us know, but Justin, let you buzz through this pre-engineered slide quick.
Yeah, so to wrap up here a little bit, to start, we know that obviously these systems, there's a lot of different aspects to these systems, and sometimes on certain jobs, those aspects need to be changed. What we want to stress the importance of is sticking with the pre-engineered system as much as we possibly can. Again, we understand that certain parts of that fan or that system may need to be changed, but when we can avoid that, we definitely want to do it. And why we want to avoid it, you're going to notice this picture with this is the built-up system. Okay, so that was manufactured. I don't even know where this was manufactured, but obviously you can see the guy wires on these fans. And the one reason why it requires guy wires is because most laboratory exhaust systems in the industry, like at Greenheck, these systems come with 125-mile-an-hour wind load rating without the use of guy wires. But that's if you use our curb. You're going to notice on the image on the left here, that curb looks nice, looks neat. Whereas if you look at the curb for this field built up system, you know, it doesn't look too stable to me, which is why guy wires would become required, and essentially there'd be no wind load rating on that system either. The biggest thing to take away between the pre-engineered and the field built up system is going to be the performance of these fans. When the pre-engineered system is at, you know, the factory, it's, you know, run through a rigorous amount of tests, meaning you know how this fan is going to perform once it gets out into the field, so there's not going to be any surprises. Once you start taking bits and pieces, you know, from different manufacturers and then, you know, making them one system, you truly have no idea how that fan is going to perform out in the field. So there could be some surprises. And you know, it could be a lot of headaches for you down the road, just because, you know, you wanted to maybe cut a few corners, you wanted to, you know, save a little bit of money going with the field built system compared to the pre-engineered system. But one thing with the pre-engineered system, yes, it is a higher purchase price up front, but it's a much lower install cost. Whereas, you know, the field built up system, it's the complete opposite. It's a lower upfront cost, but it's going to be a higher install cost. Okay. And we just can't stress the importance, especially when it comes to these life safety applications. We want to make sure that these fans are performing exactly the way, you know, we told you they were going to perform once they get out into the field. Sticking with that pre-engineered system is the best way to do that. Whereas if you look at that field built up system, not saying it's not going to work, but at the end of the day, you know, you truly don't know how it's going to perform just because it was simply never tested as a complete fan assembly. So that's, you know, kind of the points we wanted to make on that pre-engineered versus field built systems. We want to stick with the pre-engineered system as much as we can.
All right, last couple before we wrap up. We can get ready for the next session. Then I have a couple photos in here of some pre-engineered fans and installations. And, you know, Justin talked about the small footprint of the inline style. And I thought this picture was a great example of why space was at a premium on this roof deck. A lot of HVAC stuff on this building. And you can see you almost need to drop in from above if you wanted to service any of these fans. But that was a cool picture. But you know, a fan with a big footprint simply wasn't going to cut it. On the other hand, if you look at a centrifugal version, you can see the magnitude and scope of how big some of these get. If you look at this gentleman in the back, relatively speaking, these are big industrial blowers with silencers. I know Matthew's done a handful of these big jobs out in the Boston market as well. Take up a lot more footprint, easier to service though, but some cool pictures of some real installations. This next session, in a few minutes, we're going to talk a little bit more about decarbonization techniques. That includes the controls and how you want to operate these. And before we get to that, I'm going to pass it over to Matthew, see if he has any questions before we take a few-minute break and get set up for session 2.